Hello everyone, welcome to our second video example related to our lecture 2, and in this example we're going to do an example on dimensionless numbers or dimensionless groups. So in the lecture I introduced the Reynolds number. We're going to use that in our example today. Reynolds number is defined as follows, which is the product of mu times V times L divided by mu, which is the dynamic fluid viscosity. The definitions of each of these variables are shown down here, and we talked about in the lecture. A quick note down here, you have seen me use a lot of this, you might have seen in the previous lectures, which is this equal sign in the square brackets. I'm using the equal sign in the square brackets to denote the fact that I'm talking about the units and not the numbers itself. So this is to distinguish between talking about the value or am I talking about the units. It does not make sense for me to put it as rho is equals to kilogram per meter cube, because rho is equals to some fluid density and it has some value associated with that. But if I'm talking about the units of rho, using a square bracket around the equal sign is what I mean by saying that I'm talking about the units of fluid density, not necessarily the number itself. So in this case, in this question, we want to show that the Reynolds number is dimensionless, given that we have the units of each of these variables above. And secondly, we are given the values for each of these variables, and we want to compute the Reynolds number. So we need to make sure that the units are consistent, and eventually we end up with a Reynolds number that's dimensionless. Let's start with the first part, the Reynolds number, and showing that it's dimensionless. So here is the dimensions of Reynolds number. It's rho VL over mu. So here's my density, here's my velocity, my characteristic length, and here's my dynamic fluid viscosity. So I put them all as fractions like we do with units. And now, before I can do anything, I want to make sure I can convert my pascals. I want to put my pascals into base units first, which is of mass, length, and time, like I have in the other variables right here. We know that pascals is Newton per meter squared. Now you can go ahead and look up the first lecture where we talked about units and what the pascal is in base units, but I never actually try to memorize what that is. I'll just go back to the definition of a pascal and then break it back down into its base units. I know a pascal is a Newton per meter squared, is force per area. That's a unit of pressure. So we know force per area, but we know a Newton, we can break that down further. Force equals to ma, so it's mass times acceleration. So let's put those units in. And now I can simplify those units, and you can see that the unit of pascals in terms of base units is kilograms per meter second squared. Now I can put that all in to what I have up there. First of all, I'm going to clean up the units on the left hand, the first few terms first, so I just have meters at the bottom. And now I have kilogram per meter second from the first three terms, rho VL, and I make a substitution for my pascals with kilograms per meter second squared, and I still have this second that remains from this second right here. Now I can start cancelling out units. My meters will cancel, my kilograms will cancel, and then I have second squared cancel with 2 seconds, which means I have what I end up with in terms of units is 1, or it means that it's dimensionless. So we have shown that the Reynolds number is dimensionless. Now in part B, we are given a whole bunch of different numbers for the variables in different units. What I like to do is we just have to make sure that all the units are consistent and they'll cancel nicely. And what I like to do is put everything in SI units, because if I have everything in SI units, everything should cancel out appropriately and what I would expect. So to convert L into SI units, L is 2 inches, and I can just convert 2 inches to meters, which is our SI unit, so I have 0.0508 meters. I can convert the velocity 20 meters per minute. The only thing here we need to convert is the time from minutes to seconds, and I have my velocity as 0.333 meters per second. In terms of density, I have 1 gram per centimeter cubed, so I need to convert my grams to kilograms and my centimeters cubed to meters cubed. 1 gram per centimeter cubed is 1,000 kilograms per meter cubed. Now this is a pretty common conversion or common value, because we know the density of water is 1 gram per centimeter cubed. It's also 1,000 kilograms per meter cubed. So you might want to have this just memorized or have it in your head that 1 gram per centimeter cubed is 1,000 kilograms per meter cubed. That way you don't actually have to do the conversions over and over again. All right, so we have these 3 variables in our SI units. Let's look at the last one, which is our dynamic viscosity, and that's the most complicated one that we have. This last variable of dynamic viscosity has the most complicated units for us to do a conversion to SI units. Here we have pound force second per feet squared. Before we can convert our feet and seconds, we don't have to convert the seconds. Before we can convert our feet to meters, we need to get our pound force into pound mass feet per second squared first. So we need to first do a conversion from our pound force into pound mass feet per second squared, and that's our 32.174. So in this case, what you see is that we have gotten rid of the pound force, given it units of pound mass feet per second squared. We can actually do one more simplification. You have 1 feet down here and can cancel the feet down here. Now we can start converting our base units. In terms of our base units, we need to convert a pound mass in the numerator, and we have a feet in the denominator. So here are the conversion factors. Make sure that we have them on the right side. Our pound mass will cancel and our feet will cancel. And eventually now I can put everything into my calculator and I get 9.74 times 10 to the power minus 4 kilograms per meter second. That's in SI units. Now I have all 4 of my variables in SI units. I can put them all back into the Reynolds number equation with the units. I have the units down here, and I'm going to show that the units will nicely cancel to give a dimensionless number. But you can just trust the numbers and you just put in the numbers to show that and just have the value itself. So rho v L over mu, I have all the values that are in SI units. If I look at the units alone, the kilograms will cancel here. I have meters cubed, cancel with the meters cubed, and then seconds cancel with the seconds. So now I just have to plug in these numbers into my calculator, and the Reynolds number comes out to be 17,400. So that's all we have for this lecture. Work hard, be smart. I will see you next time.